Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the chemical potential for ideal gas and Fugacity. As a demonstrating example, we first talk about the chemical potential of an ideal gas. As discussed in the last task, the chemical potential is defined as. From this relation, we conclude that mu equals mu Tp. In other words, chemical potential can change with pressure and temperature. Hence, for a given set of values of pressure and temperature, mu only changes when the amount of substance changes. But what is the relation for change in chemical potential when pressure changes? Considering an ideal gas, we have the following partial differentials. Integrating between reference pressure P0 and the pressure of the gas, where mu0 is a function of temperature and is the chemical potential of the gas and the reference pressure. The values of mu0 are tabulated for different values of temperature. Equation C shows that chemical potential is proportional to the logarithm of pressure for ideal gases. Using equation C along with equation A, we can write where G0 equals G P0 equals N mu0. Equation D implies that for P equals 0, the value of G and G0 tends to be minus infinity. A strange result. Actually not, since when pressure approaches 0, then volume would increase and hence entropy would as well. Therefore, Gibbs function should decrease since G equals H minus Ts. We now talk about Fugacity. Let's rewrite the chemical potential for ideal gas as equation E is based on an ideal gas assumption. This equation on a semi-logarithmic plot shows the linear variation of chemical potential versus the logarithm of pressure, where Ct is a function of integration. Since the pressure P can take on values from 0 to plus infinity, the log P term of this expression and thus the chemical potential has an inconvenient range of values from minus infinity to plus infinity. This equation also shows that the chemical potential can be determined only to within an arbitrary constant. One can ask this question: what quantity could replace pressure for real gases while the linear relationship still holds? In other words, we are interested in a thermodynamic intensive quantity that can replace pressure but approaches pressure when gas behaves like an ideal gas. For example, under very low pressure. Lewis proposed a function f or Fugacity as the quantity of interest. Therefore, we have the chemical potential for real gases analogous to equation E as. Because of the above considerations, it's advantageous for many types of thermodynamic analysis to use Fugacity in place of the chemical potential, for it's a well-behaved function that can be more conveniently evaluated. The Fugacity is seen to play the same role in the general case as pressure plays in the ideal gas case. Fugacity has the same units as pressure. Substituting equation F into equation B gives integration of equation G while holding temperature constant can determine the Fugacity only to within a constant term. However, since ideal gas behavior is approached as pressure tends to zero, the constant term can be fixed by requiring that the Fugacity of a pure constant equals the pressure in the limit of zero pressure. That is, equations G and H then completely determine the Fugacity function. Okay, that's all for this task. Thank you very much and see you next time.